Okay, welcome to Let's Get to the Marks, going through the GCSE Combined Science Trilogy, Chemistry Paper 1, Higher Tier. This is from 2022. It's got 7 questions. Let's go. This question is about salts. Green copper carbonate and sulfuric acid can be used to produce blue copper sulfate crystals. 1.1. Excess, in bold, copper carbonate is added to sulfuric acid. Give 3 observations you would make. 3 marks. Why don't you press pause on the video, grab some paper and a pen, have a go, then unpause and watch the answers. All right, let's get into the answers. So if we have green copper carbonate and sulfuric acid, and we want to produce blue copper sulfate crystals, if we add excess copper carbonate to the acid, what 3 observations would we make? Well, the green copper carbonate would react with the acid, and eventually we would see, because it's excess, we would see green copper carbonate floating or green powder floating. So green powder floating, floating or suspended in solution. So basically, you're going to see this green powder just like, yeah, let's get rid of the suspended. You're going to see the green powder there, right? The solid green stuff floating. Also, it's a carbonate. What do you know carbonates give off when they react with acids? So you should know they give off carbon dioxide. Now, don't say you'd see carbon dioxide because carbon dioxide is colorless. So you can't say, oh yeah, I'll see, you know, a colorless gas. You can't say that. What you've got to say is, I'll see bubbles of gas forming. And of course, that is the carbon dioxide we're talking about. You can call that effervescence. It's a fancy word for buzzing, fizzing, we can say. What else would we see? Well, if you react copper carbonate with sulfuric acid, you're going to make copper sulfate. So we're going to say copper sulfate solution forming, which is blue. You should know you've used copper sulfate before in class, and that's blue. So there's quite a few different things you could say that you would see. Of course, you could say I'd see bubbles and then the bubbles would stop, or you could say um, I'll see the solution turn blue from colorless to blue because it starts off colorless. Sulfuric acid is colorless. So there's a whole bunch of stuff you can say. Anywho, this would get you 3 marks. Ba-da-ba. How can the excess copper carbonate be removed? So think about it. You've got this salt and water because that's what you make when you neutralize a carbonate with an acid. But now you've got this solid green copper carbonate floating around inside our water and salt. In fact, we said we've made copper sulfate. So we've got copper sulfate solution, which is blue. Copper sulfate's a blue crystal salt, and that's floating around in water. And we've got this green copper carbonate. How do we get rid of the excess copper carbonate? You know the coup. You're going to filter it off, and you can probably just describe, if you don't say the word filter, with a funnel and filter paper. So yeah, that's going to give you a mark. The pH of the solution changes during the reaction. What is the pH of the solution at the end of the reaction? So think about the start of this reaction. What is in there? They told us that sulfuric acid was in there, H2SO4. Do you remember the pH of acids? Acids, especially sulfuric acid, which is a strong acid, have like a pH from 1 to 6, but sulfuric acid would more likely be pH 1 or 2. It's a very strong acid. Now, what happens when you're adding the copper carbonate? Copper carbonate's a base. So what happens when you add a base and an acid? Think about it. Acid plus base, what do we call that type of reaction? You guessed it. So we should expect to see a pH of 7 at the end, because at the end of the reaction, there's no acid left. All you have is salt and salt and water have a pH of 7. Copper carbonate and sulfuric acid react to produce copper sulfate. What type of reaction is this? So they're telling you here, base and acid. What's the name? It begins with an N. Hopefully you can get it. It's neutralization. Whenever you react an acid and a base, you have a neutralization reaction. So bish, bash, bosh. Let's move on. Okay, ammonium nitrate is a salt. Figure 1 shows the maximum mass of ammonium nitrate that can dissolve in 100 centimeter cubed of water at different temperatures. The maximum mass of ammonium nitrate that can dissolve in grams per 100 centimeter cubes of water, and here is the temperature. So just to give you an example, at 10 degrees, the maximum amount of this salt that we can dissolve if we have 100 centimeters of water at 10 degrees is sort of around 27 or 28 grams. So that's how you're going to read the graph. Let's see what they want us to do. A student adds ammonium nitrate to water at 80 degrees until no more dissolves. The student then cools 100 centimeters of this solution of sodium nitrate from 80 to 20 to produce crystals of ammonium nitrate. Determine the mass of the ammonium nitrate that crystallizes on cooling 100 of this from 80 to 20. So the keys here are for us to go, right, 80 degrees, 20 degrees. What is the mass formed when we cool from 80 to 20? They keep mentioning 100, but the graph is for 100, so we don't need to worry too much about that 100. Let's go up and check it out. Right, we were given two temperatures, so hopefully you can work out what you got to do here. You're going to draw a line up from 80 degrees at the bottom to here, and you're going to read off the temperature here. Now, in case you don't know with graphs, you've got you've got a value of 10, and we've got 5 squares, so we're going to do 10 divided by 5. Each square is worth 2, so this is 84. And that is 84 grams. So you're going to get 84 grams in 80 degrees. But let's say you then cool it down to 20 degrees. How much is still going to be dissolved in the solution? How much is going to have come out? So we draw our line up. It's 1 square up as far as I can see. So that's 32. So when you cool it to 20 degrees, only 32 is left dissolved. The rest will have formed crystals inside the glass or the beaker. So how much has formed crystals? How much mass has come out? Well, 84 minus 32 grams, we're going to get 52 G of ammonium nitrate crystals have come out of the solution when we cool it from 80 to 20. This is a 3 marker. If they see that you've drawn lines up here to there, lines up from here to there, you're going to score a mark, even if you get your working out on your other parts of the answer wrong. Okay, let's zing on. That was worth 3 marks. So we know the result here. The mass was 52 grams, is the amount of ammonium nitrate crystals that formed out the water when we cooled it to 20. Now we're on to question 2. This question is about electrolysis. Figure 2 shows the apparatus used to investigate the electrolysis of potassium sulfate solution. We have 50 centimeter cube measuring cylinders. We have oxygen coming off in one. We have hydrogen coming off in the other. We have inert electrodes, these black lines here. We have potassium sulfate solution, not melted or liquid, but solution. We have a power supply, and that is that. Let's zing down and see what the actual question is. Potassium sulfate contains K plus ions and SO4 2 minus ions. In case you can't see that, that is the K plus ion, and the SO4 it shows us is 2 minus, like that. What is the formula of potassium sulfate? In what combination would these guys get together? What you have to do is you have to look at the electrical charges and you have to multiply either of them so that they cancel out. So if I have SO4 2 minus, I need to make 2 plus. And as each potassium is +1, I need to multiply potassium by 2 so that I have K plus and K plus, which will get rid of this 2 minus. So when you're making compounds, you want to cancel out the overall charge so there's no charge. Of course, if you're an ionic compound, there might be an overall charge sometimes on certain compounds, but that's different. They're ions. Right, so our formula is going to be K2SO4. And you can see that is that one there. Super. 2.2. What are the volumes of gases collected in the electrolysis experiment? Volume of hydrogen gas in centimeter cubed and our volume of oxygen gas in centimeter cubed. So what this is testing us on is, can we read the measuring cylinder? So what we need to do there is go up and see if we can read that measuring cylinder. Da, 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 da. I'm going to zoom in a bit so we can get a better read. And here we go. What is the volume of hydrogen gas and what is the volume of oxygen gas? It tells us these are 50 centimeters. So we know that each of this is 50, this is like 40, this is 30, 20, 10, 0. So we know as this is a 50 centimeter measuring cylinder, we should be able to work out how much we have, and 50 there. So we can tell we have 30 centimeter cubed of hydrogen. And how much oxygen do we have? If that's 0, 10, 20, we can tell we have 15 centimeter cubed of oxygen. So let's go and put those in to the correct place. Uh, hold on, hold on, hold on. I want to shrink this down a bit, otherwise I'm not going to be able to read the next question. Okay, so the hydrogen was 30 and the oxygen was 15. Now let's go down, and that gets us just 1 mark because they're stingy. Now let's go down here. A student made the following hypothesis. The volume of gases collected in this electrolysis experiment are in the same ratio as the hydrogen atoms to oxygen atoms in a water molecule. Explain how the volumes of gases collected in this experiment in figure 2 support the student's hypothesis. Use your answer to question 2.2. Well, look, we can see um, the volume of gas is collected in a 2-to-1 ratio as 30 centimeter cubed of H2 is double the 15 centimeter cubed of O2, of oxygen. So we have double the amount. And then in a water molecule, a molecule, the formula is H2O. So it is in the same ratio. So yeah, it is in the same ratio as the atoms or elements within a water molecule. And I mean, you can do, if you wanted to show this mathematically, you can do like 30 and 15. The ratio is 30 to 15. So we divide both by the smallest and we go 30 over 15, you get 2, 15 over 15, you get 1. So it is in a 2-to-1 ratio, which is exactly the same as the hydrogen and oxygen in water. Boom. 2.4. The experiment is repeated 4 times. The volumes of oxygen collected in the 4 experiments are 6, 9, 10, and 11. The mean volume of oxygen collected in the 4 experiments is 9 centimeter cubed. The measure of uncertainty is the range of a set of measurements about the mean. What is the measure of uncertainty in the 4 experiments? So we've been told the mean is 9, and we've been told that where are we? The mean volume of oxygen collected in the 4 experiments is 9 centimeters. We've been told the mean is 9, and the lowest result bush is 6 centimeters. So how much is that? That's -3. And the top result is 11 centimeters, which is plus 2 centimeters. So is it going to be plus 1 centimeter cubed, plus or minus 2 centimeter cubed, or plus or minus three? Well, it's going to have to be plus or minus 3 centimeter cubed because it actually goes down to 6 centimeters at the lowest point. So yeah, there's up to a 3 centimeter drift around the mean or range around the mean. So it is going to be plus or minus 3 centimeters. We can't say plus or minus two, even though it's plus two there, because it could be up to three. 2.5, the potassium sulfate solution has 0.86 grams of potassium sulfate dissolved in 25 centimeter cubed of water. Calculate the mass of potassium sulfate needed to make 1 decimeter of solution. This is one of the most important 3 marks you will get in your C1 paper. This has come up in about 6 of the last 7 C1 papers, and you need to know this equation off by heart. Unlike physics, you will not be given this equation in some sort of equation sheet. You need to know mass over concentration times volume. And you need to know this for combined chemistry. Very important, comes up a lot. So if I know what the mass is, and my mass is 0.86, that's my mass. And I know my volume is 25, calculate the mass of potassium sulfate needed to make 1 decimeter of solution. So what I need to do here is say, work out my concentration, and that will be the answer essentially. So I have 25 centimeters as my volume. We have a problem. In chemistry, we use decimeters. I need to convert this into decimeters. So I've got to do 25 over 1,000. I'm using my magic triangle, so I want to go mass over volume equals concentration, and that is going to give me the mass in 1 decimeter. So 0.86, going to divide that by 0.025. Whack that in the calculator. 0.86 divided by 0.025. Oh my days, 0.86 divided by 0.025. That is going to give me 34.4 grams. Lovely jubbly. So if you know this triangle off by heart, when you get mass and you get volume, you're going to be sorted. And you might say, but how did this didn't say it was concentration. But if they're asking you how much is in 1 decimeter, that's exactly what we do with concentration. So although we say, yeah, there's 34.4 grams in a decimeter, that means the concentration is, we've essentially found out the concentration is 34.4 grams in every decimeter, which is concentration. So cool. One for the conversion, one for the right rearrangement of the triangle here, and then one for the correct answer. Okay, we've got a 6 fat bad boy marker here, so let's have a little look at it. Plan an investigation to find the order of reactivity of 3 metals. You should use the temperature change when each metal reacts with hydrochloric acid. So what we're looking at here, we've got like, we're going to say, measure out the same mass of each metal. Make sure it has same surface area, e.g. use powder every time. So we're going to use the powder of the metal because then it has the same surface area. Very hard to control surface area, but there we go. So we're using the same mass, i.e. 1 gram of each metal. So I could put an example. I like to put an example, e.g. 2 grams of each. So there we go. I've given the examiner a number. That's going to one of my control variables. Make sure it has the same surface area each time. What we want to do now is we're going to see how it reacts with hydrochloric acid. We're changing the metal. That's our independent variable. So we want to keep the concentration and volume of hydrochloric acid the same. So use same volume and concentration of, was it hydrochloric acid? It was indeed HCl. I'm going to use the symbols because it's quicker for me, but that means hydrochloric acid. When you put AQ, all acids are in AQ. So HClOQ is hydrochloric acid. Now, whenever you're going to say use the same volume, unless you're changing the concentration, it's the independent variable, you might as well say and keep the concentration the same. And if you want to get fancy, you could say, oh, I'm going to use 50 centimeter cubed of acid. And you could just give a concentration, all right? So I'm going to give 0.5 mole DM to the -3. You actually don't need to give, just say use the same concentration and volume. You don't need to give the numbers, but this is me just being a bit of a ponce. Okay, so what are we going to do now? What we want to do is measure, well, we're going to say for the acid, we should really say measure it out using a measuring cylinder. Ugh, it's all a bit long, isn't it, really? But there we go. Right, measure out the acid using a measuring cylinder. Um, what should we say? Level on a table. Oh, we need to say wear goggles because they haven't said don't talk about safety. Wear goggles as acid is corrosive. You don't really need to explain to the examiner it's corrosive, but I'm saying wear some goggles because of it. Um, Pour into a polystyrene cup. Why are we putting acid in a polystyrene cup? It's because it is a good insulator. So put that in a polystyrene cup in a beaker surrounded with cotton wool. Um, Now we want to put a lid on beaker. Oh my gosh, can't write. With a hole through for thermometer. So essentially what this is going to look like for you guys thinking, what the hell is he on about? We've got our beaker here. We've we've already poured our acid in. Sorry, that's our polystyrene cup. Let's pretend we've poured it out the beaker into there. Now I've got it sitting in a beaker with extra cotton wool. Now polystyrene is an insulator and the cotton wool is an insulator. So they're going to reduce heat loss because we're using the heat change to measure how reactive our acid is. We're going to poke a hole in our cardboard lid. We're going to put a thermometer in there and we're going to wait for a few minutes so that we can get the temperature of the acid. We need to wait a few minutes for that. So let's say measure the starting temp of the acid. So we're now going to measure the starting temperature of the acid and then cool. And then what we want to do is then add the metal powder and stir 3 times, record the temperature every 30 seconds, plot on a graph to find the highest temperature change. So what you're essentially doing is you're going to record the temperature every 30 seconds. You're writing that down, you're plotting it on a graph, and by using your graph, you'll be able to find out where the temperature was the highest and how much it went up. And what you can do then, or you can just stare at the thermometer and write down the highest temperature you got in 5 minutes. And then what we're going to do, we're going to repeat 3 times and find an average. So we're just going to say repeat 3 times using each metal. Find a mean temp change for each metal. Okay, I'm kind of run out of room here. So how do we find out what one's the most reactive? The more reactive the metal, the larger the temperature change. So you want to find the mean temperature change for each metal. So you can do it 3 times for each metal. You're going to repeat the whole process with each metal, obviously using new acid and everything each time. And don't forget, I've kind of run out of room, but we could mention the polystyrene cup or the cotton wool we've used because it is an insulator. And all of this info is going to get you a lovely fat 6 marks. Okay, question 4. This question is about group 7 elements. What are group 7? I can't speak properly. Jeez Louise. What are the group cell? My gosh, I'll try again, shall we? 3 times lucky. What are the group 7 elements known as? And of course, you should know they're known as the halogens. And just like the group 1 metals, you have to know their name, the alkali metals, and the group 0 elements are known as the noble gases. And they're the 3 groups you have to know from the periodic table for chemistry paper 1. So if you don't know them, get them on a revision card. 4.2, why do group 7 elements react in similar ways? So it's not just the group 7 elements that all react the same as each other. The group 1 alkali metals all have similar reactions to each other. The alkaline earth metals in group 2, they all react similar to each other. So why do elements in the same group react in the same way? And it's because um, they have the same number of outer shell electrons. And that happens to be 7 electrons in the outer shell. They all have 7 in the outer shell, and so they all react in the same way. Right, let's go down to 4.3. Figure 3 shows the structure of a molecule of chlorine oxide. So we have a chlorine atom here and we have an oxygen atom here. What is the molecular formula of the chlorine oxide molecule in figure 3? So how many chlorine atoms are there? And hopefully you can see there are 2. So I would go with Cl2. And then how many oxygen atoms are there? 1, 2, 3, 4, 5, 6, 7. So we're looking at Cl2, O7, and that's the molecular formula. And that will get you a mark. The molecular formula shows you the exact number of each element found within a compound or molecule. Okay, got a little graphy. Figure 4 shows the melting points of some group 7 elements. Melting point, and then we have fluorine, chlorine, bromine, iodine, astatine. And we have the negative numbers here, positive numbers there. They're going to ask us to complete. The melting point of fluorine is minus 220. Complete figure 4. You should complete the scale on the y-axis. Okay, so we've got to complete the bars. Draw the bar for the melting point of fluorine. Right, so I need to complete the scale on the y-axis. So obviously, I think it told us that fluorine, I'm going to need to write fluorine's melting point down. It's down here, it's minus 220. Okay, so just remember that in your head. Fluorine is minus 220. I need to remember that. That means that I've got to get down at least to 220. So let's do this scale. It looks like it's 50 for each centimeter. So minus 150, minus 200, and minus 250 is going to cover us because we just want to go to minus 20. You're going to need to work out how much each square is worth. So there are 5 squares and the value is 50. So we do the value over the squares. So 50 divided by 5, each square is worth 10. So I've got 200 and I want to go 2 down to go to minus 220. And I need to draw my little bar for fluorine. Now they've done it sort of 2 in. So I'm going to go down like that. And then I'm going to go across and then go back up here. And there's my fluorine bar. Roughly, I'm in the right place. And that should get me all the marks. So 1 mark for completing the scale. I guess 1 mark for the bar. So was it 3 marks or was it 2 marks? Anywho, there we go. Let's zing down. You should complete the scale on the y-axis, draw the bar. Yeah, we got both of those right. Okay, let's move on to 4.5. 4.5, explain the trend in the melting points of the group 7 elements. So if we look at the group 7 elements, astatine's at the bottom of the group, iodine's next, then bromine, then chlorine, then fluorine. So actually, as we go down the group, fluorine's at the top of group 7. So group 7 looks like this, folks. You have fluorine, you have chlorine, you have bromine, you have iodine, you have astatine, right? Now, as we go down, as we come down, as you go down that group, you can see the melting points or boiling points go up. So as you go down the group from fluorine down to astatine, the melting or boiling points go up. Why is that? Well, let's take a little look as to why that happens. You're going to get 1 mark for describing it. So explain the trend in the melting points of group 7. They haven't told us what the trend is, so you know one of these 3 marks is for just saying the trend. So I'm going to say, as we go down the group, the melting point increases. Now they did say use figure 4, so that's my second mark. Um, Fluorine is minus 220. Now, what I want to know is I need to know one of the others because it says use the data. So it goes from minus 220 to astatine, which is roughly 300, 305. I reckon it's like sort of halfway. So I'm going to say, as we go down the group, the melting point increases. Fluorine is minus 220. At the bottom, astatine is 305-ish, I believe, if my eyesight doesn't deceive me. So that should have got us two of the marks. Now, why is it? Explain that. Why is it increasing? Well, there's a reason. The molecules are getting larger, so the weak intermolecular forces um, are getting stronger down the group, more energy needed to overcome. Now, it's not the bonds that are getting stronger. So let me just, this bit's quite difficult, but essentially fluorine's quite a small molecule. And here's my fluorine. When we want to melt fluorine, we do not break that bond. That's a very strong covalent bond. We're not breaking that. In fact, the fluorine bond is the strongest bond out of all the halogens. So why has it got a smaller melting point? Because fluorine molecules are actually quite small. And so they only have weak intermolecular forces between the molecules, which are dead easy to break. Whereas if you take a bigger one, like iodine, which is the fourth one down the group, so it's got a lot more shells than fluorine. Fluorine's only got two shells, iodine's got five electron shells, so it's a lot bigger if you were to draw it out. Iodine's bond is actually weaker than fluorine's bond, but that's not the point. When you're melting iodine, you're not trying to break this bond, you're just trying to break the intermolecular forces. And because iodine is bigger, it has stronger or more intermolecular forces, which are more difficult to overcome. So that's your reason. Okay, let's have a little look at 4.6. What is the state symbol for bromine at minus 50? Is it aqueous, gas, liquid, or solid? So what we have to do is come up here, and this is really testing you. Do you understand what melting point means? So if this is the melting point of bromine, when does it become liquid? Melting point's when you become a liquid. So chlorine becomes a liquid at minus 100, bromine becomes a liquid at minus 5. So at minus 50, bromine is solid. It only becomes a liquid at minus 5 degrees. So it's a solid. Evaporation and boiling occur at the surface of bromine at its boiling point. Name one more process that happens at the surface of bromine at its boiling point. This is a very hard conceptual bit of science, but when something is bubbling away and boiling, okay, when something is bubbling away and boiling at the same time as particles evaporating and leaving the surface, we have particles coming back and joining the surface and condensing. So at the surface of bromine, we have evaporation. We're also going to have condensation. So condensation. So we've got some of the gas particles turning back into liquid at its boiling point. Next. This question is about structure and bonding. Figure 5 represents part of a carbon molecule. Name the type of carbon molecule in Figure 5. 1 mark. This is actually called a carbon nanotube. You could call it a fullerene. Hopefully, both of those will get you the mark. Certainly, fullerene will. This is definitely a fullerene. Now, let's zing down. Suggest one property that makes the carbon molecule useful in nanotechnology. So, it has a very large surface area, and all nanotubes and nanotechnology generally revolves around the fact that they have a very high surface area. Now, you could say high surface area to volume ratio if you want to be really funky. Conducts heat well, so it's a good heat conductor. Conducts electricity, so they can be used in nanotubes, can be used in circuits. And they also can be used as nano cages. You might have heard of that. Uh, Used as a nano cage. So the theory is that we can use these molecules to trap certain medicines like anti-cancer drugs, and they'll be able to be carried around in the blood, like being carried around in a little boat, and then they can go to their target cells and destroy them. So nano cages as well for holding things. And also it's incredibly strong because of its high tensile strength. So any of these would have got you a mark. Let's zing on. Okay, we're on 5.3. An alloy of aluminium contains small amounts of other metals. Explain why other metals are added to aluminium. So here is a diagram of aluminium. Aluminium is soft. Any pure metal is soft. And if you push it, the layers can slide over each other like this. And this makes it very malleable and easy to shape into things like the bodies of cars or the frame of a bike or a cutlery set or something. However, sometimes we want our metal or our alloy of metal to be very strong. So what we do is we add other elements that have different sizes, like this little black element I've added. And what that will do by adding other elements, it disrupts the layers. And now the layers can't slide. They just can't slide past each other, and it makes the alloy much stronger than the pure metal. And so it's very good for use in things where strength is needed. So what we want to do is say um, other metals um, have different sizes and so disrupt the layers, and so the layers cannot slide, making the alloy stronger. Now, there is also the fact that sometimes you don't just want to make the alloy stronger, sometimes you want to make it resistant to attack. So aluminium is fairly unreactive, but we might add a really unreactive metal to it, like silver or chromium or something, or platinum, and that would mean that it will be even less reactive. So we could add other metals to get new properties, and that might be able to get us a mark as well. But most of the marks are going to be for saying other metals have different sizes, disrupts the layers can't slide, making it stronger. So here are the 4 marks. Different sizes, disrupt the layers cannot slide, it's stronger. 5.4, figure 6 represents the structure of a polymer. So here we have polymer chains. Compare the bonding within the chains with the forces between the chains in the polymer. So this is quite interesting and quite a difficult question. So if we look at the chain of a polymer, it has very strong covalent bonds in the chain. So in the chain are strong covalent bonds holding the polymer together. So these are very strong, and we tend not to break those with polymers. When you try to melt a plastic, and plastics aren't that hard to melt, you're actually not breaking the strong covalent bonds that hold the monomers within the polymer together. So very strong covalent bonds holding the monomers, it's just another key word, in the polymer together. Now, what I want to say next is, however, there are weak, however, there are weak intermolecular forces between the chains. So what do I mean by that? I mean, well, if you have your chain, here's my chain with very strong bonds. So this is the strong and their covalent bonds. But in between two chains, remember we did the halogens with iodine, fluorine, chlorine. We've got weak dot, and we show a dotted line for this, weak forces holding together. So it's actually easy to break two chains apart, two layers apart. So what are the marks for here? Well, saying that there are strong bonds within the polymer. However, there are weak forces in the chains. So strong covalent bonds is 2 marks holding the monomers together. However, weak intermolecular forces between the chains is the 3rd mark. There we go. Okay, we're on to question 6. This question is about hydrogen chloride and hydrochloric acid. Complete the dot and cross diagram to represent the bonding in hydrogen chloride on figure 7. Use O's and crosses to represent the electrons. You should only show the electrons in the outer shell, which is great news because if you go to your periodic table, chlorine is in group 7, so we know it has 7 electrons, and hydrogen has these numbers, so it's only got 1 electron. So all I need to do for hydrogen, I'm going to put an X, and then for chlorine, I'm going to put an O. Hydrogen only wants 2 because it just has an inner shell. That will make it happy. Chlorine has 7 and it's borrowing 1 off the hydrogen. So there we go. Correct amount, correct use, bish bash. And that's a covalent bond. Hydrogen chloride dissolves in water to produce hydrochloric acid. Hydrochloric acid is a strong acid. What is meant by the term strong acid? So you need to know this off by heart. If you don't know it, make a revision card. Strong acids fully ionize in water. You can say in solution, or you can say in water, same thing. And I'll draw a little equation to show you that. So hydrochloric acid is a liquid, but that's just AQ. All acids are AQ, not liquid. So if you dissolve them in water, they're going to fully ionize. Hydrogen chloride is actually a gas, but when it's an acid, it's AQ, and you'll only come across it as an acid really in GCSE. So there we go. It fully breaks apart to form hydrogen ions and chloride ions. We call that ionizing. Some people like to use the word dissociation, like dissociate, spreading out, separating. So you could say it fully dissociates in water, or you can say fully dissociates in solution, hence the AQ. 6.3, describe how magnesium can be used to distinguish between a strong acid and a weak acid of the same concentration. Well, we kind of already looked at that a little bit by doing the temperature experiment. We could do the temperature experiment that we did with a polystyrene cup and the thermometers. Place a thermometer in 2 sets of the exact same volume of each acid, the stronger the weak acid, at the same mass of magnesium, measure the temperature. One with the biggest temperature change is going to be the strong acid because it's going to react faster. However, it's going to be more exothermic, so you're going to get more heat given off higher temperature. What we can do is we can add the magnesium to each acid. Obviously, we want to use the same amount, but we're not doing a big 6 marker here. It will bubble more. Remember, it's going to release hydrogen gas with acids and metals. You form hydrogen gas, it will bubble more. Fizz, if you like the word fizz, more with the stronger acid. So that's one way to do it. It's much more accurate to measure the temperature, and the one which gives off the most heat will be the strong acid. Okay, 6.4, the concentration of hydrochloric acid is increased by a factor of 100. What is the change in pH? Let's imagine our hydrochloric acid is, let's just pretend it's pH 1. They're asking you, how many pHs will it change? Well, each factor, each pH is a factor of 10. So actually, scrap that. If I'm pH 5 and you increase me by 10, if you make me 10 times stronger, I'll be pH 4. If you make me 10 times stronger again by adding 10 times the hydrogen ions, I'll be pH 3. So if we have increased by a factor of 100, the change in pH is 2 pHs. Each pH, each pH decrease is an increase in the hydrogen ion concentration by a factor of 10. Now we might say, why is it 2 marks? So we need to read this carefully. The concentration of hydrochloric acid, they've increased it by a factor of 100. So yeah, what is the change in pH? So it's not just that it changes in 2 pHs. We want to say its pH goes down by 2 because you actually get stronger and more concentrated when you go down. So its pH goes down by 2. So if it was pH 5, it will now be pH 3, which is 10 times 10, factor of 100. I longed out that explanation, guys. Leave a comment if you're absolutely baffed, and I'll get back to you. Right, 6.5. Ethene and hydrogen chloride react to produce chloroethane. The displayed formula equation for the reaction is ethene plus hydrochloric acid goes to chloroethane. The reaction is exothermic. In the reaction, the energy released forming new bonds is 56 kilojoule greater than the energy needed to break existing bonds. Calculate the bond energy of X. So this is quite a difficult one, but it will be made clear. So we have, whenever you have these, the clue is reactants take away the products equals the energy change. You have to know this off by heart. So if you don't, get it down and then you'll be fine with this question. So it is reactants minus products equals energy change. So all we've got to do is add up all these bonds from this table to add up all the reactants, add up all the bonds from this table to get the products. Now we know, sorry, the products are over here. We know that that equals the energy change. So that equals minus, what did it say? 56. So we know that. And so what we're going to do is add these numbers up, write them down. You get 1 mark for working out the energy in the products, 1 mark for the reactants, and then you're going to need to rearrange, simplify to find the missing bond energy. So we don't know that bond, but we can work out the other. So I've got 4 413s. Look, there's one there, one there, one there, one there. So I'm going to go 413 times 4, and that is going to give me 413 times 4 equals 1,652. And then I don't have this, so I can't work that out at the moment, but I can work out this HCl. It's 431. So I want to do 1652 plus 431. So let's smash that in the calculator. Calculator. Never heard of a calculator, but there we go. So I'm left on my reactant side. I've got 283 plus CC because we don't know that. So that's the reactants. Now I need to work out my products because it's going to be minus my products. So let's work out the products. I've got 1, 2, 3, 4, 5 HCs. So I want to put my working out over here. 5 times 413. So let's do that. 5 times 413 equals 2065. Now, on the mark scheme, some of these big numbers appear and you'll be picking up marks for the working, even if you flop the rest. There's 2 other bonds. Don't miss this bond, the CC bond. That is 346. And then don't miss this bond, the CCl, sneaky little bond in there. So plus 339. Let's smash that all together and find out what that equals. So plus 339 plus 346. So this is what I got. I got 2,750. And then that is equal to minus 56. Now you might say to me, sir, how do you know it's minus? Well, it was told here. The reaction, the energy released from forming new bonds is 56 greater than the energy for breaking. And what you have to know is that bond making is endothermic, which is a plus sign, and bond, wrote that the wrong way around, guys. Excusez-moi. Bond breaking is endothermic, and bond making or forming is exothermic, releases energy, so it has a negative sign. Yeah, anywho, right. Let's solve this. Now, if the examiner sees 283 or 2750 anywhere in your working out, you're bashing in 2 marks. So well done because you've already got a level 7 on a very difficult question because you got 50%. So what we want to do now is simplify. So I'm going to take 283 from each side. So I'm going to go minus 283 from each side is my first step. So let's do that. Let's go minus 2083 from each side. And that is going to get rid of my 2083 there. And I'm going to go minus 56 minus 2083 equals that equals that. So what I'm going to do is now have C minus 2750 equals minus 2139. Now what do I want to do? Well, I've got minus 2750. I want to get rid of this and leave the CC on its own. So I'm going to add 2750 to each side. So add 2750 to each side. And what do I get if I do that? I'm going to end up with plus 2750, and that equals bish bash bosh. That equals my CC is going to equal 600 and 11. And that is the answer, 611. Okay, we're on to the last question now of this paper. So this question is about elements and compounds. 7.1 figure 8 shows a reactivity series. Most reactive at the top, least reactive at the bottom. We've got potassium, magnesium, metal Y, carbon ion, hydrogen, and copper. Give the method and conditions used to extract metal Y from a compound of metal Y. So how would we get metal Y out? There's a couple of methods we could use to get metal Y out of a compound of metal Y. You might think, what the hell are they on about? They're saying, how could you get Y away if you had like, I don't know, YO2? So if it's in a compound like YO2, how do you get the Y out? Well, you could displace it with a more reactive metal. So you could heat the compound of metal Y with magnesium in a displacement reaction. So we would say heat the compound of metal Y in a displacement reaction with a more reactive metal, such as magnesium. And that's going to get us both the big fat marks that we want. However, we could also use electrolysis, which is, of course, what we use a lot of the time for extracting reactive metals, because you don't want to waste an expensive metal like magnesium getting metal Y out. So we could do electrolysis, which we would say pass current through the molten compound. And so you have to melt the compound of Y. So the molten compound of Y. So if it was YO2, you'd melt it down so the oxygen ions and the Y ions are free to move. And then they're going to be able to be moved to the electrodes. Um, God, it's late at night and I'm tired. 7.2. I'm trying to get all of these papers done before the exams this year. Sodium reacts with titanium chloride, TiCl4, to produce titanium. Complete the equation. You should balance the equation, 2 marks. So if I've got sodium plus titanium chloride, sodium is obviously more reactive. This is a displacement reaction like I was talking about. So we're going to get NaCl because it's more reactive. It's group one. So it's going to form a one-to-one with that. Why, you say? Why? Well, group one elements have a +1 charge when they become ions and they react in compounds, and group 7 elements have a -1 charge. So they cancel each other out in a 1-to-1 ratio. So the formula is NaCl. If it had been magnesium chloride, magnesium's in group 2, it'd be 2 plus and you'd have MgCl2, but such is not the case. And then we will have the titanium, which we have extracted. So what I need to do now is balance it. Well, we've got 4 chlorines there, so I need to put a big fat 4 here. And that means that I need a big fat 4 there. So 4 sodiums, 4 chlorine on that side, 4 chlorine on that side, 4 sodiums, 1 titanium, bish bash bosh. We are balanced. 7.3, the reaction between sodium and titanium chloride is a redox reaction. Write a half equation to show the sodium is oxidized in this reaction. So redox means this. And you'll probably, when you think of redox, you need to remember this little, whatever it's called, it's not a mnemonic, whatever the hell that is, oil rig. And that means oxidation is loss of electrons. It's always annoying this because oxidation is also the gain of oxygen when you've got oxygen hanging about, but reduction is the gain of electrons. Some people like to say LEO, grrr, i.e. loss electrons, oxygen. Sorry, loss of electrons is oxidation, and grrr is gain reduction. Cool. Okay. I prefer oil rig for obvious reasons. You'd have to do the grrr, the lion's roar. Okay, write a half equation to show that sodium is oxidized. So we want to show that sodium is what? Oxidized, losing electrons. So we want to write Na here. It's oxidized. So we're going to draw an arrow and then show it losing electrons. So we draw it as Na plus, and then we put plus E minus. Now, I'm going to put the older symbols in there. So yeah, Actually, I'm not going to put symbols. We don't need symbols for this. But there we go. Sodium goes to sodium plus plus E minus, and that's 2 marks. Bish bish. I'm on to 7.4. We got our big fat calculation, 6 marks, lovely jubbly. 108 grams of aluminium. So immediately train yourself. So when you're going through exams, you immediately in chemistry, you spot the data, you circle it, you write that's mass. Reacts with 1.2 kilograms of copper, that is mass, to produce copper. The equation for the reaction is 2 to 3, 3 to 2. So we've got all the ratios that we need there. Calculate the maximum mass of copper produced in grams. You should determine the limiting reactant, the relative atomic mass. As soon as I see AR and MR, and I've already written mass, boom, this is what it triggers. Mass in my magic triangle, dividing line over MR times number of moles. So what I need to do now is work out how much aluminium I've got and how much copper chloride I've got in moles, check the ratio and see if it fits this ratio. If it doesn't, work out which one is limiting, which one do I not have enough of to react. And then after that, we can calculate the maximum amount of copper produced. So let's do this bit first of all. So my aluminium is 108 grams. And I want to do mass over MR to work out the moles. The MR, AR of aluminium is 27. So we're bussing out 108 over 27. So we go 108 divided by 27. And that is, I have 4 moles of Al. Beautiful. Now I need to work out my mass of copper chloride. And guess what? They've been so generous. They've given me the copper chloride is 134.5. So I know that I have 1.21 kg. What's the little mistake here? I need to times this by 1,000 because it's not in grams. So that's going to get me an extra mark. So I now have 1,210 grams. I'm going to divide that by 134.5 and 1210 divided by 134.5, and that is going to give me 8.996. I think at this point we can just call that 9 moles, right? So I've got 9 moles of copper chloride and I've got 4 moles of aluminium. Now I just want to tell you how many marks out of the 6 you'd have got so far. Working out the moles of aluminium is 1 mark. Doing the conversion of kilograms to grams is 1 mark. Working out the moles of copper chloride is 1 mark. You'll have picked up a big fat 3 marks, even if you flop from here on out, all right? That's 50%. That's a level 7. Bosh. Right, let's move on. Now, which one of these is limiting? I know what you're thinking. Aluminium's limiting. There's less of it. There's only 4. We don't know that yet. We've got to check the ratio. So the ratio of aluminium to copper chloride is 2 to 3. What does that mean? That means for every 1 mole of aluminium, I need 1.5 moles of copper chloride. Or for every 2 moles of aluminium, I need 3 moles of copper chloride. Well, I've got 4 moles of aluminium. So I need to have 4 times 1.5, or you can say times, if you prefer to do this, times 3 over 2 equals 6 moles of copper chloride. So really, I need 6 moles of copper chloride needed. So 6 moles of CuCl2 needed. Do I have 6 moles of copper chloride? You bet I do. I've got 9 moles. So I'm actually going to have 3 moles in excess. So the copper chloride has 3 moles in excess, but they wanted the limiting. So I want to point out aluminium is limiting. So aluminium is limiting. And that is going to get me. I've just worked out what the limiting reactant is. It isn't because it had less moles. It's because once you do the ratio, yeah, you don't have enough. Or I've got enough copper chloride and I'm going to have left over 3 moles of copper chloride. I need 6 moles of copper chloride to take out and react with that aluminium, and I'll have 3 moles left. Okay, so what do we want to do next? The final part for the final 2 marks is to say, well, calculate the maximum copper that you could make in this reaction. I mustn't use this 9 here with the copper chloride because this is in excess. that is not going to tell me how many moles I can make of copper. Why? Because a lot of this, 3 moles of this, is going to be left over. So I actually use the 4 moles of aluminium. You use your limiting reactant to find out how much product you can make. After all, I can only make as much product as I have aluminium. So the ratio of aluminium to copper is the exact same ratio as the aluminium to copper chloride. So I know I can only make 6 moles of copper. We needed 6 moles of copper chloride. We can only make 6 moles of copper. So the ratio is 2 to 3. So I can make 6 moles of copper. So now all I need to do, I know my moles of copper is 6. I know the MR of copper I've been given here is 63.5. So I'm going to do 6 times 63.5. And that is going to give me 381 grams. And there you go. Your last 2 marks are for working out the moles of copper, which was 6, and the 381 grams. And that's your 6 fat marks. They threw the 133.5 in there. We didn't even need it. Cheeky gits. Last couple of marks. Sodium metal and sodium chloride are both able to conduct electricity. Describe how sodium metal conducts electricity. Excuse me while I cough my guts up. Okay. So what is it that sodium metal has? Sodium metal has delocalized electrons. Yes, you can say free electrons if you are studying AQA. Sodium metal has delocalized electrons, 1 mark. They carry charge through the structure. Now, in AQA, they will generally let you have it for this, but the better way to word it is this, but it's an extra line. So don't know whether you want to do that, but sodium metal has delocalized electrons, which can move through the structure. So the electrons themselves are moving through the structure, and on their way through the structure, they can pick up and carry charge. There we go. Don't say current. They don't let you say current. Explain how sodium chloride can conduct electricity. So this is a little bit different. Sodium chloride is a giant ionic lattice, and it can't conduct electricity unless you melt it. So we have to say you need to melt the sodium chloride so it is molten. The ions are then free to move. It's very important that the ions are free to move, and you have to melt it first. And if they're free to move, this allows charge to flow. Woo. So your 3 marks are for saying either use molten or melt it. Means the ions can move freely, allows charge to flow. And that's the end of the test. Don't forget sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. Come on, people. The exams are coming.
You're still here? It's over.